Starting. All right, so now we're in back to finding derivatives, and the algebra that we're going to learn on this one, it's going to be like the perfect dessert for the lunch that you'll just had. Okay, let's try it out. Example 4. For each of the following, find dy dx, which of course means what? Derivative. That's Leibniz notation. And then simplify it after the fact by factoring out least powers, okay? Which is basically pulling out, you'll see, pulling out the GCF, the greatest common factor. All right, so part A, we've got y equals x squared times the square root of 1 minus x squared. This function has a domain if we wanted to figure it out. Let's do that real quick. It's a good review. All right, we have a square root. 1 minus x squared has to be greater than or equal to 0. Yes? Would y'all agree? Square root of positive or square root of 0? Now, that is a quadratic inequality. It cannot be solved algebraically. Remember that in pre-cal? It was harped on. So we have to solve it graphically. So you can factor it if you want. You can bring the negative out and do this. And now if you want, you can multiply both sides by -1 and flip the inequality. It's entirely up to you. I'm just going to say that this function is a parabola. It opens down, right? And what's the y-intercept? 1, right? Yeah. So here's 1, and it opens down like this. And if I leave the negative intact because it opens down, I want to know where it's positive. So that's going to be between the x-intercepts. So how do I find the x-intercepts? Well, a couple ways. You can either factor x squared minus 1, it's the difference of two squares, or you could just look at it, right? At this point, y'all can tell what the roots are. What are they? 1 and -1, yeah. Now let me show you what you cannot do, just to review. If you did factor this, it's a difference of squares. This is still okay. It's still fully intact. But now what you can't do is say x minus 1 is greater than or equal to 0 or x plus 1 is equal to 0. That's where students get in trouble because that has these pointing both to the right. That would be x is greater than -1 and x is greater than +1, which is really just x greater than 1. So don't do that. Don't do that. So now I know the domain is going to be, do your math homework, right? The set of all x such that, and what's cool about the connected interval is you could say -1 less than or equal to x less than or equal to 1. You can actually pretend like x is right here on the interior and you write it in increasing order. So when you do the compound inequality, which is this one here with the three parts, x is always in the middle and they're always less than or equal to, always. It's always for the and case, all right? Small number on the left, big number on the right. Or, of course, you can write it in interval notation, x epsilon. This is a little bit easier, right? -1 to 1. So that's just a pre-cal problem, algebra problem, but it's always good to know where a function exists. It would be kind of egg on our face if we were talking about it where it didn't exist, right? Oh, man. Right. Okay. Let's take the derivative now, shall we? To take the derivative, to get to BOTC, if you will, I need to rewrite this in some kind of form. So for sure, since I have a radical, I need to get rid of the radical. So I'm going to write that as 1 minus x squared to the 1/2 power. Now, can I distribute the x squared inside there? No, I can't. Right, I can't. But can I expand the binomial to the 1/2 power? Square multiplied double square and then divided by 2? Is that how that works? No, I can't distribute that. So this is as simplified as it gets. So no worries. I can take the derivative of this. What's the rule out of the box? Something times something. Product rule. It's a product rule. Okay. And this, for some reason, the product rule is the one that students typically mess up on. Don't mess up on it. Okay. Remember, there's a way to take inventory. You have two factors, which means you're going to have two terms. Each term has its own derivative of one of the factors only. I'm going to go ahead and start with the first one. I take the derivative of the first one first. And don't forget the all-important left side. dy dx equals the derivative of x squared is 2x times this one goes along for the ride. Goes along for the ride. And then plus x squared goes along for the ride times the derivative of the second. Now, the derivative of the second one is going to require what rule? Chain rule, because it's composite, right? Blob to the 1/2. So now by the chain rule, we're going to get 1/2 times blob to the negative 1/2. Right? And see how I did that again? 1/2 blob to the negative 1/2. And then I write the blob in there. Times the chain rule, the derivative of its blob. What's the derivative of 1 minus x squared? Negative 2x. Close that. And then close this. So there you go. I had two factors. Now I have two terms. Yay. Yay. So I took the derivative, but you know what? If I wanted to use that now to answer some questions, it's not a very useful form, is it? I mean, it's kind of ugly. It's kind of ugly. And it's okay to call it ugly. You can't hear you. It doesn't have ears. Okay. It's inanimate. Let's clean it up. You want to clean it up? I want to clean it up. You know, it'd be really nice, not only if we cleaned it up, but you see how it turned into two terms? It'd be nice if we can get it back into a single factor dude. Because if it's factored, remember, we're setting it equal to 0 more than likely, and then we can use the zero product property. So, all right. First step is just to go through and do a little housekeeping. Get rid of unnecessary parentheses that were there for safety reasons. Pull constant multiples out front, all that good stuff, right? Housekeeping. So here we go. dy dx equals, in the first term, not much I could do except drop the parentheses, right? And I'm not going to put it back in radical form, okay, because I want to be able to factor out least powers. Now, the second term, that's where it's at, right? What can go on there? Let's see. I have this -2 times that 1/2. Those divide out, right? But I am left with a negative. See that? I'm left with a negative x times this x squared, which gives me a negative x cubed. So minus x cubed. I'll put that in front. And that takes care of everything except the 1 minus x squared factor. 1 minus x squared to the negative 1/2. Okay. I cleaned up nicely. Ready for prom, yeah? All right. Now let's factor. When we factor, we pull out the greatest common factor. And we pull out numbers and we pull out variables. Let's see, what would be a good color for factoring? How about this nice salmon color? All right, so do we have any numbers besides 1 or -1 that we can factor out? Now, do we have an x? Yeah. Now, what can I factor out x-wise? X to the first. Okay, let's review why that happens. This is really x to the first, and this is x cubed. So their GCF is going to be the lesser of the powers, right? The lesser, because there's only 2. Usually we say the least power, but it's the smaller of the 2 exponents. So we can pull out an x. Now look at this other factor. This is where it probably hasn't happened for you before. We do have this other binomial factor, 1 minus x squared, but they have fractional exponents. But they do in fact have some portion of that factor in common. Using the same idea, what can we pull out? 1 minus x squared to the what power? No, negative 1/2, because it's less, right? See that idea? I was able to pull out an x to the first because 1 is smaller than 3. I have a 1/2 and a negative 1/2. Negative 1/2 is indeed smaller than 1/2. You pull out the lesser or the least power. Magnitude doesn't count. It's actual sign, okay? Now, from there, I usually step up my notation. I go with kind of a beefy bracket, and maybe this is time for the beefy brown bracket because we want to take inventory of what's left. I have two terms to start with, yes? See that? I'm going to have two terms to end with. Now, when you factor out, you're really dividing out, right? Factoring out is really dividing out. Factoring out is really whating? Dividing out. So let's come off to the side to our little workbench over here. I factored out an x times 1 minus x squared to the negative 1/2 from the first term. So off on my workbench here, it's really what I started with, 2x to the first, 1 minus x squared to the 1/2, and I factored out, so I'm dividing out x times 1 minus x squared to the negative 1/2, okay? That's what I did. This is what I started with. And then this is the GCF, using the lesser of the two powers on both. All right, so now, I mean, eventually you should be able to do this in your head. But for now, we're going to do it on our workbench, right? So what am I left with? I'm left with 2, because that's 2 divided by 1. And what happens with the x's, Ella? They divide out. There we go. They divide out to give you 1. Nice. So that's not the big deal. Here's where the newness comes in. What am I left with this factor? Well, using the rule of exponents, that's, well established. When I divide and the bases are the same, and they are, I do well with the exponents. I subtract them. So 1/2 minus negative 1/2. Don't let your brain betray you. It's 1/2 minus a negative, which really becomes 1/2 plus 1/2. What's a half plus a half? 1 whole. There you go. 1 whole. That's what's left in the first term. So let's come over here and write that. 2, come on, 2 times 1 minus x squared. Minus, now let's see if we can do this one in our head. This one will be a little bit easier because the funky fraction divides out. But what am I left with? When I take an x out of an x cubed, I'm left with x squared. And that's because x cubed divided by x is x squared. Okay, good. And what am I left with on this funky factor? Not 0, 1. That thing perfectly divides out with that, so I'm left with 1. And we don't need to write the 1 because it's the identity element of multiplication. Now you could have gone off to the side and done workbench division as well. Let's see how we could have come up with that exponent right here of 1 without going off to the side on the workbench. It's real easy. Just do it in your head. What you started with should be written on top, and what you're factoring out should be written on the bottom. So it almost looks like division, doesn't it? You can almost imagine like there's a division bar right here. Imagine it. And then just do the subtraction in your head. 1/2 minus negative 1/2, that's 1. Boom. Okay. It will become easy. Right now, it's just fun. Okay. Or maybe it's already easy. So notice what that does. It puts it back in factored form. And now all we have to do is do one last bit of housekeeping. I have a negative exponent, so I have created a denominator. That middle factor, the funky factor, is to the negative exponent power. So it goes back in the bottom. And since this is my final cleanup, I'm also going to put it back under the radical. So that's going to become in the denominator 1 minus x squared. All right. If you want to highlight it as we go, take inventory. It's not a bad idea. There's not much to keep track of, but we do want to be diligent, right? Diligent. Someone this morning said they were not participating, and I said, hey, why aren't you participating? And this is like an all-year thing. He's like, oh, I don't even want to be at school. I don't need this stuff. I like to code. I'm like code? Like you like to do, huh? I don't know. I don't know his name. He hasn't even participated. I don't know his name. And I was saying, man, there's coding all over this place. Mathematics is the template for coding. And man, you have to be so detail oriented in a code. You can have 3 or 4 pages of code and one little symbol in there is wrong. And the code doesn't do what you want it to do. Same thing here. You got to be diligent. So are you going to actually be doing these problems when you're graduated from high school or college, or like in your career? You're going to be doing this? No, no. But what are you going to take with you that you've earned in this class? Problem solving ability, right? Sisu, you care, you're thinking, you're broadening your horizons. Every single experience that you have makes you better informed for decisions that you're going to make in the future, right? You are a sum total of all of your experiences, okay? So you try to get as many of those as you can. Try to get as many of those as you can. And if you're going to be somewhere, you might as well participate if you're there, right? And you might as well participate as much and as actively as you can, because the time is going to go by faster, right? If you're bussing tables rather than just, standing at the front of the restaurant waiting for people to come in. Industry, right? When you're being industrious, man, you'll be surprised what fortune will come your way, right? All right. So that's the denominator. And let's see what we have in the numerator. I do have the X that's out front. Is it even worth highlighting? I guess, red. And then look what's left in the beefy brown brackets. I'm going to put another factor, but I'm going to downgrade it to a parenthesis. We do have to distribute, don't we? And now we can, because it's to the first power. So what are we going to left with? 2 times 1 is 2. And then watch this. Minus 2x squared minus the x squared that's afuera. What happens? Minus 3x squared. Kaboom. It is now back in factored form. If we needed to set it equal to 0, you see what we did here? 2 minus 2x minus this 1x squared minus 3x squared. If I needed to set it equal to 0, I could just set these 2 factors equal to 0. In fact, I already know it's going to be 0 and plus or minus the square root of 2/3. Got them. And then where is it undefined? Well, it's undefined when the denominator is 0. But remember, there's a whole host of values here. But notice there is one value. There is one value that is in the domain of the function that's not in the domain of the derivative. What is it? Or 2, I guess I should say. See how this radical is in the numerator here, but on the derivative, it jumps to the denominator where we now can't divide by 0. You can take the square root of 0 in the numerator all day long, but now it jumped to the bottom. So the domain of the derivative is always going to be either the same size as the function or smaller. We can't use 1 or -1, can we? We can't use 1 or -1. In fact, there's probably vertical tangent lines at 1 and -1. Yeah, I'm guessing this graph only lives between -1 and 1. And when it comes out of the x-axis, it comes out vertically, almost like a semicircle. That's what I would imagine. Okay, the function's defined there. Remember, we defined continuity from one side, but not differentiability. Pretty awesome, right? All right, I want you to try letter B on your own. Okay, I'm going to work it up here quietly with the recorder going. If you get stuck, maybe sneak a peek, but slow and steady, right? Diligence. Sisu. Ooh, should we talk about the strategy to begin with? Yeah, good. We're faced with something immediately. Do I use the Hody-High rule, or do I bring it to the top and use the product rule?
It's not a constant.
Boy, those are the 2 reasons that I was going to point out. Yeah. First of all, the numerator is not a constant. So if I bring it to the top, it's not going to be as easy as it were for a constant, where it would just be a chain rule. I would turn it into a product rule, okay, which we just did. It's not a big deal. But as we just saw, the product rule will always generate two terms, okay, if you have two factors. If you recall the Hody-High rule, it does generate two terms in the numerator, but overall, it's all over a single denominator. So it actually does create just a single termed fraction. And if you had to factor out least powers, it would only be in the numerator. So that's what you picked up on. So there's benefits to both, right? But remember, as you go forward from this day on, that the Hody-High rule gives you a single term, whereas the product rule gives you multiple terms. So I'll let you try it however you feel. You don't want to just sit there and not do anything, right? That's probably the worst way to do it. Bell is going to catch us, but I went ahead and we'll see the conclusion of this problem tomorrow. I went ahead and did the Hody-High rule. So I do have a single term, but I will have to factor out least powers in the numerator of my single term, okay? If you did the product rule, then you won't even have a denominator, which is going to look very similar to the previous problem. Yeah, so you can keep plugging away at it until the bell rings. It's about a minute and a half, but I'm going to stop here in terms of instructional purposes. Thank you, those of you who were at the Commons today. There was nobody there, but I already got a couple of emails back from some teachers who said this is a great idea. Thank you, Math Club, for doing it. So check that sign up list if you're on there. We're not going to do Wednesdays because Wednesdays are, that's when we have our meetings and other people have meetings too. So if you signed up to do a shift, just show up there tomorrow for advisory and look for kids. They'll be looking for you, and then have them fill out that form when I emailed it out to the group, have them fill out that form to show that they were there. We'll keep it going. It'll gain popularity once people hear about it. And once they hear about how awesome y'all are, they might just want to come and spend time with you.